Hey everyone, and welcome to another explainer. Today, we're going on an absolutely incredible journey. We're going to trace an X-ray from its very conception at the electrical wall outlet right through the machine and directly into the patient's body. For all you BMRIT students tuning in, it's a fascinating story of power, physics, and ultimately protection.
Okay, let's dive right into this, because mastering this physical transformation isn't just about passing your next physics exam, it's honestly the ultimate key to patient safety. Every single knob you turn and every setting you adjust fundamentally changes how electricity behaves and consequently how radiation interacts with human tissue.
Here's our roadmap for today's explainer. We'll be looking at 1. Powering the tube. 2. Taming voltage ripple. 3. The physics of attenuation. 4. Filtration for safety. 5. Beam restriction. And 6. Essential takeaways. Section 1. Powering the tube, specifically focusing on the high-voltage DC supply. You see, before we can even dream of creating a diagnostic X-ray, we have to secure a highly stable, controllable, high-voltage direct current supply. The historical progression of X-ray generators we see here is pretty stunning. Early single-phase generators were incredibly inefficient because their electrical waveform literally drops to 0 twice per cycle. That gives them 100% ripple. Three-phase generators improved things dramatically, dropping that ripple to somewhere between 3.5 and 13%. But the modern standard that we rely on today, those are high-frequency generators. Moving to Section 2, taming voltage ripple and creating smooth electrical waves. Let's see how this builds as we pivot from the heavy generator hardware itself to the actual invisible electrical waves it produces. To really wrap our heads around this, we have to define voltage ripple. Think of ripple conceptually as a bumpy road for electrons. High ripple means the tube voltage is varying wildly. Because of this, electrons are hitting the anode at varying, inconsistent energies. This creates a much wider, lower quality energy spectrum that is totally inefficient and ultimately degrades your image. So, the absolutely crucial point here is that modern high-frequency generators achieve less than 1% ripple. By converting the AC main supply to a high-frequency AC and then rectifying it, we get a nearly constant potential. We get a smooth road. This delivers a highly consistent beam quality and significantly lowers the radiation dose to the patient, all while keeping the exact same image quality. All right, Section 3, the physics of attenuation, or what happens when X-rays enter the body. Let's shift our narrative focus entirely. The perfectly powered X-ray beam has now left the tube and is hurtling through the air, heading straight toward the patient. Just pause and think about that for a second. What actually happens when X-rays enter the body? Well, the patient's tissue fundamentally alters the beam. Some photons are absorbed entirely, some are scattered away, and some passed right on through to the detector. And this brings us to a brilliant piece of math, the Beer Lambert Law. It tells us that the intensity of the X-ray beam drops exponentially. This drop is based on the material's linear attenuation coefficient, which is just dictated by tissue density and atomic number, and the physical thickness of the body part it's actually passing through. We connect this math to our clinical reality using the half-value layer, or HVL. For a typical 80 kVp beam in soft tissue, the HVL is around 3 to 4 centimeters. Basically, a higher HVL means you have a more penetrating or harder beam. It's an absolutely critical measure of beam quality. Next up, Section 4, filtration for safety and protecting the patient. Because before that beam even touches the patient, we have a huge opportunity to intervene. Let's look at one of the most massive safety mechanisms built right into the machine, filtration. Notice the striking difference here. An unfiltered beam is packed with low-energy, soft photons. These photons are entirely useless for the image, simply because they don't have the energy to make it through the patient to the detector. If we left them unfiltered, they'd be absorbed directly into the superficial tissues, doing nothing but burning the patient's skin and adding unnecessary dose. By adding a filter, we harden the beam and dramatically lower that dose. Now, what's really interesting here is this exact number, 2.5 millimeters. Under standard guidelines, like those from the AIIMS, a minimum of 2.5 millimeters of aluminum equivalent filtration is a strict legal mandate for general radiography. Aluminum is essentially the perfect bouncer here. It effectively absorbs those weak, low-energy photons while remaining relatively transparent to the high-energy ones we actually need to make the image. Moving to Section 5, beam restriction and aiming the X-ray beam. So we've got incredibly clean electrical power, and we have a wonderfully filtered, hardened beam.
Now, how do we physically aim it precisely at the anatomy we actually want to see?
Enter the light beam collimator. This device sits just below the tube and features 2 pairs of independently adjustable LED shutters. It brilliantly uses a light and mirror system to project the exact rectangular shape of the X-ray field directly onto the patient. So you can see precisely what anatomy is going to be irradiated before you ever even think about pressing the exposure button.
There are 3 sequential, incredibly critical reasons why radiographers absolutely must aggressively restrict the beam to only the necessary anatomy. First off, you instantly reduce the patient dose. Second, by irradiating a smaller tissue volume, you drastically reduce the amount of Compton scatter created. And third, less scatter reaching your detector means a beautifully improved high-contrast image. And that brings us to Section 6, Essential Takeaways and the Physics Checklist. We followed the electricity from the wall, shaped it, smoothed it, filtered it, and aimed it. The journey of the beam is complete, so let's quickly consolidate our core lessons.
Here is your final physics checklist. For all the BMRIT students watching, you're definitely going to want to commit this directly to memory.
Rapid fire, let's lock it in. High-frequency generators are the modern standard, yielding clean power with less than 1% ripple. The Beer Lambert Law maps exactly how tissue attenuates that radiation. A mandated 2.5 millimeter aluminum filtration safely hardens the beam. And tight collimation is your absolute best tool to reduce both unnecessary dose and image-destroying scatter. Ultimately, all of this complex math, the electrical engineering, and the strict safety hardware comes down to a single profound truth you should take away today. Every image carries physics in every pixel. The real question is, how well will you wield that physics for your next patient?